All right, 12.3, the tangent line problem. Now we're going to talk about the slopes of tangent lines and the limit and derivatives. So the tangent line to a graph at a function f at a point is the line that best approximates the slope at that point. So as you go around a curve, the slopes are going to change. Determine the rate at which a graph is rising or falling at a single point is the slope of the tangent line at that point. You can visually approximate the slope, just like you did in early algebra, just by looking at the change in y and the change in x. So let's visually approximate the slope of the tangent line to this parabola at the point x equals 3. So you can see we have the point x equals 3 there, and the y value is 3.3. And then we look for another point to help us to estimate the slope. And I look for a nice solid point. Let's say this one right there. And then we look for the change in y and the change in x. So that is at negative 1, 2. So negative 2 to 3.3. So that's 5.3. And then the change in y is from 1 to 3. So that's a change of 2. So we know our slope is 5.3 over 2, or 2.65. All right, so that's just what you did in Algebra 1, estimating your slope just by counting it. Now, there is also finding the slope by using a limiting process. So a secant line is a line through 2 points on a graph. So if you look over here, you see the red secant line. And we took 2 points. Our first point is at x, and then the y value would be the f of x, whatever it is. And then we move over some. So this point is x plus h for the x, and then the y value is f of x plus h. All right, so there you have 2 points. So pause here and find the slope between those 2 points. Just plug them into the slope equation. All right, so you should have gotten f of x plus h minus f of x for the y values over the x values, which are x plus h minus x. You might recognize this, that the slope of the secant line is actually the difference quotient. All right, now if we bring these 2 points together, that is, we make h become nothing, the difference between the 2 points becomes nothing, then we get the slope of the tangent line. So if we take the limit as h approaches 0 of the difference quotient, we get the slope of the tangent line, which is what we want. All right, there is an address for an applet where you can move the points and look at how you get the tangent line. But there's our equation written out, typed out nicely. The slope of the tangent line to a curve is the limit as h approaches 0 of the difference quotient. All right, so we're going to use that process to find the slope of the tangent line to the graph of the quadratic x squared plus 5x. So we just plug it in, limit as h goes to 0, and pause there, and pause here, and you guys try to plug it in and see how you do. And then let's see, that would be x plus h squared plus 5 times x plus h minus x squared plus 5x. And I prefer you guys use the parentheses there when you do the subtraction. So then we're going to just write it out, square that out. X squared plus 2xh plus h squared plus 5x plus 5h minus x squared minus 5x over h. And then the f of x is going to actually all subtract off. So you have the limit as h goes to 0 of 2xh plus h squared plus 5h over h. And then you can cancel your h's in each term. So you have 2x plus h plus 5. And finally substitute your 0 and you get 2x plus 5. So for any point on the graph of this parabola, this will be the slope of the tangent line at that point. So now let's use it to find the slope at the point 1, 6 and the slope at the point 2, 14. So if you think about the parabola, so 1, 6, it'll have a slope, and 2, 14, it'll have another slope. So if we plug in at 1, 6, x is 1, so the slope is 2 times 1 plus 5, 7. And at the point 2, 14, the slope is 2 times 2 plus 5, or 9. So you guys know you have a point and a slope. It's really easy to find the equation of a tangent line, which if you remember from chapter 10, was a little bit longer of a process with the parabolas that we had in chapter 10. All right, now the derivative is, a calculus thing, and the derivative is the limit as h approaches 0 of the difference quotient. Ha! So the limit is the slope of the tangent line. That is what a derivative really is. Right? And you'll notice I've added just one notation here. We use f apostrophe x, and it's pronounced f prime of x when you read it to mean the derivative. So sometimes you'll also see the derivative called the instantaneous rate of change of a function. So if you ever see anything in the question that asks you for the instantaneous, that's going to be the derivative. Right? So let's find the derivative of 9 minus 2x cubed. So again, we're going to do the limit process. So you go ahead and plug that in and give it a try, and then come back and we'll see if we agree. All right, so limit as h approaches 0 of 9 minus 2 times x plus h cubed minus 9 minus 2x cubed all over h. And then, of course, we have to remember our binomial, and Pascal's triangle will make that a lot easier. 9 minus 2 times x cubed plus 3x squared h plus 3xh squared plus h cubed minus 9 plus 2x cubed over h. And keep writing your limit until you plug that in. 9 minus 2x cubed plus 3x squared h, minus 6 x squared h minus 6 xh squared minus 2 h cubed minus 9 plus 2x cubed all over h. And the 9 and the 2x cubed are going to cancel right off the front. And then we have our h's are going to cancel in each term. So we have the limit as h goes to 0 of negative 6x squared minus 6xh minus 2h squared. And our h is out of the denominator now, so we can just do our substitution, and we get negative 6x squared. All right. Plug them in, multiply out, cancel off, and then plug in your h. All right, so last one we have to do is I have to give you one that has a root in it because they're done a little different. Well, they're simplified a little differently as we did in the last section. So give it a try. Pause here, plug it in the difference quotient. All right, so if we take that negative through, the 2's are going to cancel out. We're going to subtract off, and we get the square root of x plus h minus the square root of x over h. And if you remember from the last section, we'll need to use the conjugate in the numerator and denominator to get rid of those radicals. And I know you're saying, oh, but we're putting the radical back in the denominator. Yeah, that's okay. That's what we want. We need to get rid of the h now. So difference of squares, when you multiply, we get x plus h minus x over, and don't actually, multiply this out. Just leave it factored form in the denominator to make your life a little easier. All right, and then we have x plus h minus x, which just leaves you with h, and then h over h is going to cancel. So that's going to be 1 over, limit as h goes to 0. Sometimes I forget to. Square root of x plus h plus the square root of x. And now, since we've canceled that h on the outside, we can actually substitute and get 1 over 2 square roots of x. And that's how you deal with a radical. Okay? All right. Have fun with the derivative.